All right, guys, Honors Chem, we are going to start a new unit today. We're going to talk about acids and bases and start learning about them and use our concentrations, molality, and molarity to help us understand what's going on. Okay, so properties of acids and properties of bases. Okay, so acids, a lot of us actually have a lot of experience with acids. Acids, they taste sour. So I don't know if you guys have ever had like Sour Patch Kids or the sour gummy worms, that crystals powder on the outside. Yes, some of it's sugar, but most of that is actually citric acid in the solid form, and that's why it tastes so sour. So acids taste sour. Okay. Another thing that we want to talk about is acids react with lots of metals. Not all of them, but they do react with most metals. So for example, if I put nitric acid in with some copper, I would get some really nasty nitrous oxide gas and some copper oxide. It would be this brown, yucky looking gas, and it's actually toxic to burn or to breathe in. So it's not a reaction that you really want to do a whole lot. Okay. We also have that acids turn litmus paper red. So they turn litmus paper red. Okay, so you can get two types of litmus paper. You can get red litmus paper or you can get blue litmus paper. If you put acids on any of those two types of litmus paper, it will make it turn bright red. If you use an indicator paper, which is sometimes called a universal indicator, so universal indicator papers will turn anything that I would consider what we call a warm color. So we would get from yellow to orange to red to maybe bright magenta pink. So acids would be warm colors, where the red to the bright magenta pink would show us the strongest acids, and the yellow would be the weakest acids. Okay, let's do some bases really quick. So bases feel slippery. So when you put a base on your hand, they're going to feel really slippery. Think about when you're washing your hands with soap. Your hands feel slippery. Why do your hands feel slippery if you've ever washed your hands with soap? Hopefully you have. Or if you've accidentally spilled bleach and you got some of that bleach on your hand feels slippery. The reason it feels slippery is bases are really, really good at dissolving fats and proteins. And what are our skin cells, the outside of our cells, made out of? They're made out of fats and proteins. So basically, the bases feel slippery because they're dissolving you, right? They're actually dissolving your proteins and your cells and the fats that make up your skin. Okay? They taste bitter. Okay, so they have a really bitter taste. So think about if you've ever had straight cocoa, like chocolate cocoa powder, not sweetened, not anything. If you've had straight cocoa powder, that stuff's really bitter. It's pretty basic. Okay, and bases turn litmus paper blue. Okay, if we use universal indicator, okay, universal indicator, just like the acids used all the warm colors, you guessed it, the bases use all the cool colors. So if I had a base, I would start with greens, blues, onto purples and the deep indigos. So in universal indicator, we would get cool colors. When you're talking about art theory, okay? So in this right here, notice if I start out with blue litmus paper, that acid turns it bright red. And if I start out with red indicator, that base turns it kind of a bluish purple, okay? So we can start with blue and red indicator papers. Most people don't use litmus paper like that anymore. They use a universal paper that has many dyes on it so that you get a whole rainbow of colors, and you can do acids and bases on just one type of paper instead of having to have both red and blue paper. Okay, let's talk about some definitions of acids and bases. Now, there are three types of acids and bases. There are Arrhenius acids and bases, there are Bronsted-Lowry acids and bases, and there are Lewis acids and bases. And if you wanted to do a Venn diagram of that, let's see if I have some room to make a Venn diagram. So if I did a Venn diagram, you guys all know what Venn diagrams are, right? We're looking at the overlap of different things and different definitions. So if I did a Venn diagram, our very smallest circle would be our Arrhenius model. And then around that Arrhenius model, these don't overlap. They completely coincide within each other. We would have our Bronsted-Lowry model. And then to be even more inclusive, we would have our Lewis model. Oh, and it didn't change to orange. This would be our Lewis model. Okay, so our Arrhenius model is our most specific model of acids and bases. And if we want to be a little bit more inclusive, we start using Bronsted-Lowry. And if we want to be really inclusive, we start learning and using the Lewis model. Okay, so they basically are packaged in each other. Okay, so let's start with the Arrhenius model. Now this model is based on the scientist Svante Arrhenius, and he was from Sweden, if I remember correctly. And he lived about 150 years ago, almost 200 years ago. 1850s to 1880s is when he was doing his stuff. The Arrhenius model states that an acid is a substance that contains hydrogen, okay? So it's got to contain hydrogen, and it's got to ionize. Remember when we put things into water, they will separate out into ions, right? It ionizes to produce hydrogen ions in an aqueous solution. So that is the definition here. So it's got to have hydrogen, and it's got to ionize, and it's got to make hydrogen ions in aqueous solution. Remember, aqueous is just a fancy way of saying water. So this is a water-based solution where things will separate and we'll get hydrogen ions in solution. Okay? So a base is kind of the same thing. It has to have a hydroxide group. And it has to dissociate, once again, break apart, which is another fancy way of saying break apart, to produce hydroxide ions in a water solution. Okay? So when we look at this, a good Arrhenius acid would be hydrochloric hydrogen chloride. When I bubble this hydrogen chloride gas up through water, I will separate into a hydrogen ion and a chloride ion. Okay? I will I will dissociate those ions, or I will ionize those ions, and I will dissociate them to produce the hydrogen ion in water solution. That is an Arrhenius acid. Okay, and then notice I have an Arrhenius base. I have sodium hydroxide solid, and when I dissolve that into water, I will get the sodium ion and the hydroxide ion, and having that hydroxide ion is an Arrhenius base. Okay, so Arrhenius acid, I have to have hydrogen ions. An Arrhenius base, I have to have hydroxide ions, and they have to be in water. Okay, did you guys see that? They have to be in water solutions. All right, Bronsted-Lowry. Bronsted-Lowry bases are acids and bases are a little bit more inclusive. So Danish chemist Johannes Bronsted and English chemist Thomas Lowry proposed a more inclusive model of acids and bases. This model focuses on a hydrogen ion. In a sense, we can also think of a hydrogen ion as a proton. Isn't a hydrogen ion without its electron, right? Hydrogen without an electron is just a proton. So sometimes when you think of a Bronsted-Lowry basis, some chemistry classes will call it a proton instead of a hydrogen ion, okay? In the Bronsted-Lowry model of acids and bases, an acid is a hydrogen ion or a proton donor. It gives a proton to something else, okay? And the base is a hydrogen ion or a proton acceptor. Okay, so we're basically just giving and accepting a proton or a hydrogen ion. So for example, if I had an acid with a hydrogen and I had that hydrogen dissociate, I could have that hydrogen join water. And if that hydrogen joins water on that, I would create H3O, positive hydronium. This is called hydronium. And I would be left with the negative ion from that acid. Now, we have the acid that we start off with, and what the hydrogen goes to is what's called the conjugate acid. So whatever accepts that hydrogen or that proton is called the conjugate acid. And then notice whatever accepts that proton is called the base. And the ion that is left over after that hydrogen or that proton is donated is called the conjugate base. Okay? So a conjugate acid is the species produced when a base, notice the water accepted that proton or that hydrogen ion. So the conjugate acid is H3O, the hydronium ion. The base, water, H3O, accepts the hydrogen ion or the proton from the acid HX and becomes the conjugate acid H3O. The conjugate base is the species that results when the proton is after the proton is donated. So the conjugate acid would be the X minus. Okay? So in this example, we have the acid of hydrogen fluoride, hydrofluoric acid, the base of water. Notice water accepts this hydrogen, right? That hydrogen becomes part of that water and we create a hydronium. And the conjugate base is just the fluoride ion that's left. Okay? So yes, water can act as a base. Water can also act as an acid. It can give up one of its protons as well. Okay? And we'll see that in a bit. So here's a physical representation of this. Notice the hydrogen joins that water to produce the hydronium ion. And the fluoride ion is just left by itself. So here we have our acid, here we have our base, here we have our conjugate acid, and here we have our conjugate base. Okay? All right. So let's look at a Bronsted-Lowry base. So if a Bronsted-Lowry acid is a proton donor, a Bronsted-Lowry base is a proton acceptor. So here we have our base, ammonia. Now I'm going to draw out the Lewis structure for this because the Lewis structure for this helps make it make more sense. And if I have water, I'm going to take one of these hydrogens and I'm going to put it right here on that lone pair. So I will make the ammonium ion, and I will be left with the hydroxide ion. Okay, so notice that the ammonia on that lone pair accepted the hydrogen or the proton from the water. So here ammonia is our base, water is acting as an acid because it's donating a proton. Our conjugate acid is the ammonium ion, and our conjugate base is the hydroxide ion. Okay, so yes, water can act as both an acid or a base depending on what it's working with. Okay, so let's identify the conjugate and acid and base pairs in each of these reactions. So what you have to look for is who is donating that proton. So let's do A together. Notice ammonium, NH4, is donating a proton to hydroxide. So, and when it donates that proton to hydroxide, we are making water. So ammonium is our acid, and the hydroxide is our base. So who accepted that proton? Hydroxide did. And so this is our conjugate acid, and the ammonia, NH3, is our conjugate base, because it's just the reverse of what the reaction is that we just did before. So take a minute, look at B and C, and see if you can figure out the conjugate acid, conjugate base, the acid, and the base. Okay? You guys ready to check? Okay, on B, who is donating a proton? Did you see that the hydrogen from hydrobromic acid was accepted by the water? Did you guys see that? So hydrobromic acid is our acid, and water, because it accepted the proton, is our base. So what has the extra hydrogen on it, or proton on it? Hydronium. So that is our conjugate acid. And bromide is left by itself, so this is our conjugate base because it doesn't have the proton on it anymore. Okay, what did you see in C? Who's giving up a proton? Did you see that water was giving up a proton to give it to the carbonate ion? So water, because it is giving up a proton, is our acid, and because the carbonate ion was accepting a proton, it was our base. Okay? So the bicarbonate ion is our conjugate acid, and the hydroxide is our conjugate base. Okay? How'd you do on that? All right. Next, we have Lewis acids and bases. And now Lewis acids and bases is even more inclusive. We'll talk a little bit more about Lewis acids and bases next year in AP Chem. Okay? Organic chemistry is all about Lewis acids and bases. Like, that's how the reactions happen. For right now, the following table summarizes the three models, and it will be sufficient. I actually want to give you an example of a Lewis acid and base once we get through here. Okay, so the Arrhenius model of an acid is a hydrogen ion producer in water. Make sure that you know that Arrhenius has to be in water, okay? The base definition is a hydroxide ion producer in water, okay? Bronsted-Lowry definition of an acid is a hydrogen or a proton donor, and the Bronsted-Lowry definition is of a base is a hydrogen or a proton acceptor. Okay, Lewis acids and bases have to do with electron pairs, lone pairs. So Lewis acid, my goodness, this really is taking a long time. Okay, a Lewis acid is going to let me scroll. Okay, Lewis acid is all about electron pairs. So Lewis acid is an electron pair acceptor. Okay, so Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So let's look at this. My classic example that I like to use is the iron +2 ion that is found in your hemoglobin. Okay, so your hemoglobin has an iron +2 ion. So it means it is short 2 electrons, and this is complex in a big network of nitrogen and proteins. Okay, when we breathe in oxygen, oxygen is O2. It has all these electron pairs sitting there. Just think, a pair would fill that +2 charge quite nicely, right? Give us oxygen. That attraction between the lone pair on oxygen and the +2 on the hemoglobin is what actually binds the oxygen to our hemoglobin so that our blood, our red blood cells, can actually transport the oxygen through our body so that our muscles and our cells can work. So our whole way of breathing and getting oxygen in and out of our cells is all about Lewis acids and bases. Okay, so in this, the electron pair acceptor would be our iron +2. And the electron pair donor in this example would be our oxygen. Okay, so that is a classic Lewis acid and base pair. Okay, now last but not least, it's been a long time since we've done nomenclature of acids, since the first week of December, right? So it's been 2.5 months. Okay, so we have had 2 types of acids, if we remember, okay? So we had binary acids. If you remember binary acids, they were just 2 elements. They were hydrogen with a nonmetal. And they were always dissolved in water, okay? Do you guys remember that? So we start with the prefix hydro. And then we use the root of that nonmetal word, and we add on the suffix ic, and we add the word acid. So for example, HF would be hydro and aqueous, right? Hydrofluoric acid. HCl would be hydrochloric acid. H2, let's do another one. H2S would be aqueous, of course, hydrosulfuric acid. Okay? So remember, if I only have 2 elements and it's dissolved in water and one of those elements is hydrogen and the other is a nonmetal, I'm going to start with the hydro prefix, and I'm going to use the root of the nonmetal and add on the suffix ic and end with the word acid. Okay? Now, ternary acids. These are our acids that are from our polyatomic ions. Okay, so we are definitely going to want to use our polyatomic chart that we have on the back of our periodic table. Okay, now if you remember, we had a bunch of polyatomics that ended in ITE. Okay, and we had some polyatomics that ended in ATE. Okay, so the 8 polyatomics become ic acids. We change 8 to ic. And the ite polyatomics become us. So we change the ite to us. So let's give you a couple of examples here. So if I had H3PO3, I would have to look and see what PO3 is. And if I look at PO3, it is phosphite. So I'm going to change that phyte to us. So this is going to be phos for us acid. If I did H3PO4, this is phosphate. Phosphate. So this would be phosphoric acid. Okay, let's do another example of this. If I had ClO4, HClO4, ClO4 is perchlorate. So 8 goes to ic, so this would be perchloric acid. Okay, if I had HClO2, this is chlorite. ClO2 is chlorite. So this is going to go to us, so this would be chlorous acid. Okay, so you really have to be paying attention to the end of the radical's name. If it's if it's ite, ITE, you're going to change it to us. If it's ate, ATE, you're going to change it to ic. Okay? Next time, we're going to talk about the strengths of acids and bases and learn which ones are strong and which ones are weak and how we can tell the difference and what that means. All right? Have a great time. We'll talk to you later. Bye.